Okay, so in this video we're going to have a look at the Leaving Certificate Higher Level Maths Paper 1 for 2015, and we're going to have a look at question 6. So question 6 is a financial maths question, and it involves Donna, who's arranging a loan and is examining two different repayment options. So he has Bank A here and Bank B here. So for Bank A, they will charge him a monthly interest rate of 0.35%, and we've got to find, correct to three significant figures, what the APR would be that is equivalent to a monthly interest rate of 0.35%. So we've got to convert this to a yearly rate. So as usual, we start with our formula here. F is equal to P times 1 plus I to the power of T. Now F is going to be our final value. P is the principal, the loan amount if you like. I is the interest rate as a decimal, and T is the time period. So in this particular case, what we're going to do is, we know that the monthly interest rate is 0.35%. So 0.35% as a decimal is going to be 0.0035. You've got to divide it by 100. Our time period is going to be 12 months. And what we're going to do here is, imagine that we've taken out a loan of €1. What would the final value be at the end of that year? If we know the final value, we can work out the annual interest rate then. So when you work this out, what you actually get is 1.04 2818. That means, so this is our final value. We've borrowed €1, and at the end of 12 months at 0.35% monthly rate, we find that we now owe €1.042818. So that means the I in this particular case, or the interest rate, is 0.042818. So the rate then, the actual the annual rate, the APR then, would be, just multiply this by 100, so that's 4.28 to three significant figures. Okay, so that's part A1. So let's look at part A2 then. Now in this particular case we have Bank B, and Bank B will charge him an APR of 4.5%. So now we have the annual rate, and what we've got to do is work backwards to find the monthly rate to three significant figures equivalent to that APR. So again, we start with our F is equal to P times 1 plus I to the power of T. Now in this particular case, we know that the annual rate is 4.5%. So in other words, if we borrow €1 over the 12 months, we know that we will owe 1.045. So just take this 4.5 divided by 100, that will give you 0.045. Now we borrowed €1, so that means at the end of the year we're going to owe €1.045 if we borrowed €1. So what we've got to do now is work out what the monthly rate would be, what this I would be. We're doing the reverse of what we did in part 1. Okay, so we got to work this out. So we got 1.045 is equal to 1 plus I to the power of 12. Now the opposite to raising something to the power of 12 is to get the 12th root of it. So what we're going to do is this, 1.045, and we're going to get the 12th root of it. Now I'm going to write it in an index form like this, 0.045 to the power of 1/12. It's the same thing as this here, and that's equal to 1 plus I. Now we got to get rid of this 1 here from the right hand side, so it's 1.045 to the power of 1/12 on the left hand side. We're going to subtract 1 from both sides. That will give me I here, and when you work that out, what you get is 0.0036748. So that's the I here. This is this value here. So if that's I, then that means the actual rate, then the monthly rate, that's equivalent to 4.5% APR would be this thing here multiplied by 100. So that's 0.367% to three significant figures. Which is fine, correct, to three significant figures, yes, that's what we were asked to do. So that's it really, that's it for part A. Let's have a look at part B then. Now, Donna is borrowing 80,000 euros at a monthly interest rate of 0.35%, fixed for the term of the loan from Bank A. The loan is to be repaid in equal monthly repayments over 10 years. The first repayment is due 1 month after the loan is issued. That statement there is important. Calculate correct to the nearest euro the amount of each monthly repayment. Okay, so I'm going to do this two different ways. I'm going to use these timelines first. So I'm going to use, going to call this time 0. Then I'll call this one here time 1. We'll put in a time 2 as well. I'm not going to put them all in, just some of them. So then we move on up to, now remember we're talking about monthly repayments here, and we're talking about 10 years. So that's going to be a total of 120 months. So I'll put in 119 and I'll put in 120 then. This is the final month here. So the main thing to remember here is that the loan amount, the 80,000 euros, is equal to the present value of all future repayments. Excuse me. So if you take any future repayment, so for example, if you take, remember he's starting to, his first repayment is going to be 1 month after he takes out the loan. He takes out the loan here. So this is when he's going to pay back his first installment. We've got to get the present value of that amount. Then we've got, this is when he pays back his second installment. We've got to get the present value of that amount. Then we've got to come down here, take the present value of this amount. And we've done all the ones in between as well, by the way. We're not just doing these 4, we're going to do all the ones in between as well, in theory anyway. So when you get the present value of all of these repayments, add them all up, they have to be equal to 80,000. We're going to make that equation and solve for A. So what is our present value? Well, if you start with P, or no, sorry, we start with F is equal to P times 1 plus I to the power of T. Now just rearrange that, you get P, which is the present value. The present value is equal to the final value, if you like, 1 plus I to the power of T. Now this F here is really these values here, the amount of each repayment. So I can just take that out there if you like, and just call it, we'll call it A for the amount that we're going to pay back, that Donna is going to pay back, the amount that Donna is going to pay back at the end of each month. Okay, so let's work this out. So the present value of this amount here, I'll put it in, let's put it in a different color here, green. So this present value here is going to be A, whatever that amount is, we got to work that out, divided by 1 plus I. Now remember, I is 0.375% as a decimal, so that's 0.0035. So I've added the 1 as well, by the way. I've just added the 1 to it. So it's A over 1.0035. What's the time period here? Well, it's just 1 month, so this is to the power of 1. So this amount here is the present value of this amount here that he's paid back in 1 month's time. So what about this amount here then? Well, that's going to be the same thing. That's going to be A over 1.0035. But now this is the present value of this amount here. Remember, this is 2 months time, so that's been that's over a 2 month period. So the time period here, we got to raise that to the power of 2. We continue, we do all the ones in between. Now we don't physically have to do them, but you can imagine that we do. And we'll move on to do these two here. So the present value of this amount that Donna has paid back is going to be, again, A over 1.0035. Now, how many months are we talking about here? Well, if you look at this one here again, we're looking at 1 month here, and this is T1. We're looking at 2 months here, and this is T2. So look, this is T119, so the power here would be 119. What about this one here? Well, this is his final repayment. That's A over 1.0035. And how many months are we talking about? Well, this is T120 in this case, so that would be to the power of 120 here. Okay, so these are all our repayments. We've left out the ones in the middle. We didn't do all of them. But if you add all of these up, if you add all of these amounts up, you will get the loan amount, which is 80,000. So this is the equation we're going to write down. So we're adding all of these amounts up here. We should get 80,000. So let's do that down here. So we're going to say 80,000 euros is equal to A over 1.0035 plus A over 1.0035 squared plus, we didn't do all of them. I'll tell you what, I will leave this one out as well. I'll just include this one here. So it's A over just the last one, 1.0035 to the power of 120. Okay, so now we've got an equation here that we've got to solve for A. Now we're missing these ones in the middle, but so we've got to employ a technique that will allow us to deal with that. So let's see what we're going to do here. First thing I'm going to do is write down the 80,000 again. I'm going to factorize out the A. You don't have to, but I think it just makes it a little bit easier. So really we've got here 1.0035 plus 1 over 1.0035 squared, and then we went all the way up to 1 over 1.0035 to the power of 120. Now what I'm going to do here next is look at these numbers here. When you look at them, you'll see that this is actually a geometric series. So what I'm going to do is add these up using this formula here, the sum of a geometric series, 1 plus r to the power of n here over 1 minus r, I should say, the power of n over 1 minus r. So this is what I'm going to use. Now in this particular case, just looking at these numbers here, I can see that my first term is 1 over 1.0035, this number here. So what's or now? Or here, what do I multiply each term by to get the next term? Well, I'm multiplying the top by 1, and I'm multiplying the bottom by 1.0035. Look, this is 1.0035, this is 1.0035 squared, the next one would be 1.0035 cubed. So what I'm doing with the bottom part, with the denominator, is multiplying by 1.0035 each time. So that's my OR. How many terms have I got? Well, this here is the first term, and I can see my 1.0035 is the power of 1. This is my second term, and I've got a power of 2 here. So this must be, this is the power of 120, so I must have an n here as my n is just equal to 120. I have 120 terms. So I have everything now that I need to put into this here. So let's do that. So again, I've got my 80,000 on the left hand side. I've got my A out here, which I need to solve for. So all I got to do now is put my figures in here, my Sn, the sum of my geometric series. Well, A here is 1 over 1.0035. I've got to multiply that by 1 minus r to the power of n. Well, r is 1 over 1.0035, and that is to the power of 120. All of that then is over 1 minus r, which is 1 minus 1.0035. And that's what I've got to solve now. So 80,000 again on the left hand side. Okay, so let's see if we can just simplify this. Now I've got an A here, and look, I'm going to just let you do this yourselves. I mean, you can raise this to the power of 120. 1 to the power of 120 is just 1. 1.0035 to the 120, power of 120 you can do on your calculator. Subtract that from 1, divide it by 1.0035, and what you get is, I've done it already, so it's 0.342471 So when we do the top line, this is what we get here. I wouldn't maybe try typing all of this into your calculator in one go. It's it's best to do it in a number of different steps here. So you can do a few different lines between here. On the bottom here you end up with 0.000035. Okay, so now almost there. So again we have our 80,000 here, and we have our A. When you divide these two here you get 97. This is multiplied here. 97.8489137. Okay, so all we've got to do now is divide these two here. So we're going to get A then finally equal to, divide 80,000 by 97.8489137, and you get 817.59 euros. We were asked to give A to the nearest euro from what I can remember. Let me just double check that again. Calculate correct to the nearest euro. So we got to work this out to the nearest euro, so that's just simply going to be 81. This is a 5, so that's going to be 818. 818 euros to the nearest euro. Okay, that's it. That's the kind of long-winded using a geometric series method for working out A. Now you can be asked to do it that way specifically. In this case we weren't, but I'll just show you both methods anyway. So what we're going to do next is do it the easier way, if you like, just using the amortization formula, so you can be specifically asked that way as well. Okay, so our amortization formula is just simply A. The amount of each repayment is equal to P times I times 1 plus I to the power of T, all over 1 plus I to the power of T minus 1. So this is a little bit easier anyway. So our P is our principal, so what did he borrow? He borrowed 80,000 euros. Okay, so let's put in all our bits and pieces here. The I here is the interest rate as a decimal. Well, it was 0.35%, so as a decimal it's 0.0035. Just divide by 100. We've got 1 plus I, so it's 1.0035. Just adding 1 to this here, if you like. To the power of T, well, it's 120 months, so we're going to raise to the power of 120. We've got 1.0035 here again, to the power of 120, that's this bit here, and then finally we've got to subtract 1. Okay, so again we have everything into our formula here. This is our A here again, by the way, so this is 80,000. Again, you can work this out on your calculator. Look, so I won't do it. You can do a few steps in between here if you want, but what you basically get on the top here, the numerator here, is 0.005322 532296, and then our denominator is 0.52 0.52 0846 0846. So what you can do here then is just divide and multiply, divide these two, divide the top by the bottom, multiply by 80,000, and you get A is equal to 817.59, which is approximately equal to 818 euros to the nearest euro. Okay, and that's it. That's the, sorry, not 818, that should be to the nearest euro here. That should be 518. 518 to the nearest euro. So that's the same answer we got in the when I did it the other way. So as I say, you can be specifically asked to do it this way. You can be specifically asked to do it using geometric series, or in this case we weren't asked to do it any particular way, so you can, whichever way you like. This is maybe the easier or the quickest way of doing it. Okay, and that's it for this particular question.